Hey there, fellow space enthusiasts. Welcome back to the deep dive. Don't forget to hit that like button and subscribe to the channel and the notification bell so you never miss out when we upload a new deep dive. Tonight, we're going to be diving deep into the fascinating world of stellar evolution.
It's going to be exciting.
It is those giant balls of burning gas that light up our universe from their humble beginnings all the way to their explosive ends.
That's right.
And this deep dive is for everyone, whether you're a UPSC aspirant, getting ready for those big exams,
Yeah.
or if you're a senior school student who just loves astronomy, or even if you're just someone who enjoys looking up at the night sky and just wondering about the mysteries of the cosmos. This is for you.
Yeah, what I think is really fascinating about stellar evolution is that it really is a story of cosmic creation and destruction.
Yeah,
A cycle that's been, playing out for billions of years. And it's really a story that's intimately connected to our own existence.
that's so true. I always find it so amazing that something as vast and seemingly distant as a star can have such a profound impact on our lives here on Earth.
Oh, absolutely.
But let's rewind to the very beginning. Where do stars even come from?
Well, stars, like everything else in the universe, they have a birthplace.
Okay.
And their nurseries are these vast, swirling clouds of gas and dust called nebulae.
Nebulae.
Mhm.
I've seen pictures of them. They look like these abstract paintings with swirls of colors and light.
Yeah, they're quite a sight to behold. And they're not just random clouds either, they're the crucibles of star formation.
Wow.
Imagine these immense clouds, mostly made up of hydrogen and helium, the simplest and most abundant elements in the universe, scattered across galaxies.
Okay, so how do we go from just a cloud of gas and dust to a blazing ball of fire like our sun?
That's where gravity takes center stage. Gravity is like the sculptor of the cosmos,
Right.
constantly pulling matter together. And over, vast periods, gravity pulls the gas and dust in a nebula, causing it to clump together.
So it's like a cosmic snowball effect.
Precisely. As these clumps grow denser, they heat up and they eventually form what we call protostars.
Protostar. So this is like the baby stage of a star.
Exactly. Imagine a protostar as a ball of gas that's getting hotter and denser by the moment.
Okay.
But there's a tipping point.
Yeah.
As the core of the protostar continues to collapse under its own gravity, it eventually becomes so hot and dense that something incredible happens. Nuclear fusion ignites.
Now, nuclear fusion, that's a term we hear a lot in science, but can you break it down for us?
Imagine tiny atoms of hydrogen, the simplest element, being forced together under immense pressure and heat. They fuse to form helium, the next element on the periodic table, and in the process, an enormous amount of energy is released.
So it's like a cosmic power plant.
In essence, yes. This nuclear fusion is what makes a star shine. And once a protostar reaches this stage, it officially graduates to become a main sequence star.
And this is where our sun comes in, right?
Precisely. Our sun, that familiar yellow orb in our sky, it is a main sequence star. It's been steadily fusing hydrogen into helium for about 4.6 billion years, and it has billions of years to go.
It's amazing to think that the very process that powers the stars also provides the light and warmth that sustains life on our planet.
Yeah.
But stars don't stay in this main sequence phase forever, do they? What happens next?
You're right. The main sequence is just one chapter in a star's life story. And what happens next depends on the star's initial mass. Let's consider a star like our sun,
Okay.
a fairly average-sized star.
Hmm.
When a star like our sun starts to run low on hydrogen fuel, it undergoes a dramatic transformation.
Dramatic. In what way?
Imagine this.
Okay.
As the hydrogen in the core gets depleted, the star's core starts to contract, and this contraction actually causes the outer layers of the star to expand outward. The star swells up enormously, becoming what we call a red giant.
So it gets bigger, but why red?
As the star expands, its surface temperature actually cools down, which shifts the light it emits towards the redder end of the spectrum.
Okay, I'm starting to see the picture here. A red giant. A giant, cool red star. But how giant are we talking?
Well, if our sun were to become a red giant, it would engulf Mercury, Venus, and quite possibly even Earth.
Wow. So that's the fate that awaits our own solar system.
It is, but not for billions of years.
Okay, that's a bit of a relief, I have to say. So what happens after the red giant phase? Is that the end of the line for a star?
It's not quite the end, but it's definitely a turning point. Red giants eventually shed their outer layers, creating these beautiful and ethereal clouds of gas and dust called planetary nebulae. But what's left behind at the core is a fascinating object, a white dwarf.
A white dwarf. Tell me more.
A white dwarf is essentially the exposed core of the star, incredibly dense and incredibly hot. It's about the size of Earth, but with a mass comparable to our sun.
So it's like the star has shrunk down to a tiny, super dense ember.
A very apt description. And over billions of years, this white dwarf will slowly cool down, eventually fading away into a cold, dark object known as a black dwarf.
So that's the fate of stars like our sun. From a blazing main sequence star to a red giant to a white dwarf, and finally, a quiet black dwarf. It's like a full circle of life and death cosmic style.
You've got it. But remember, this is just the story for stars like our sun.
Right.
What about stars that are much larger, much more massive? Their journey takes a completely different turn, leading to a far more dramatic and explosive end.
Now you've got me on the edge of my seat. What happens to those massive stars?
Instead of quietly fading away, they go out with a bang. We're talking about supernovae, the most powerful explosions in the universe.
Supernovae. Now that's a term that evokes images of like cosmic fireworks and unimaginable power. Tell me more.
Imagine a star many times more massive than our sun reaching the end of its life. It's exhausted its nuclear fuel, and gravity is no longer counterbalanced by the outward pressure from nuclear fusion. The core collapses in on itself at incredible speed, and then
What? What happens next?
Then, boom! The core rebounds in a cataclysmic explosion, sending shockwaves through the star and blasting its outer layers into space with incredible force. This, my friend, is a supernova.
Wow. It's hard to even comprehend the scale of such an event. But wait, are all supernovae the same?
Not exactly. There are different types of supernovae, each with its own unique story.
Oh,
One type involves a white dwarf in a binary system where it's siphoning matter from its companion star.
so it's like a cosmic vampire, feeding on its stellar neighbor.
That's one way to put it. And as this white dwarf keeps accumulating matter, it eventually reaches a critical mass, and then boom, a type IS supernova.
So it's like a cosmic case of too much of a good thing.
Exactly. Now, another type of supernova called a type 2 supernova involves a single massive star that's simply run out of fuel in its core.
So no vampire stars in this scenario.
No vampires here. This is all about the internal struggle of a star against its own gravity.
Okay.
As the core collapses, it triggers a chain reaction, leading to a rebound shockwave that blows the star apart.
So a dramatic implosion followed by an even more dramatic explosion.
You got it. And these supernovae are incredibly bright. For a brief period, a single supernova can outshine an entire galaxy.
That's just mind-blowing. So all this talk about exploding stars and cosmic destruction, is there anything positive that comes out of a supernova?
That's a great question, and the answer is a resounding yes. Supernovae play a crucial role in the universe's evolution. They're responsible for scattering heavy elements, like carbon, oxygen, and iron, into space.
Hold on. Heavy elements, why are those important?
Because these heavy elements are the building blocks of planets, of life itself.
Really?
Without supernovae, we wouldn't exist.
Whoa. So we're literally made of stardust. That's incredible.
We are indeed. Every atom in our bodies, except for hydrogen, was forged in the heart of a star that lived and died long ago. That's a profound thought, isn't it?
It really is. It makes you realize that we're all connected to the cosmos in ways we're only beginning to understand.
Exactly. And speaking of connections, let's talk about what's left behind after a supernova.
Okay.
It's not always just an empty space.
Okay.
Sometimes the core of the star collapses further, forming something even more extreme.
Okay, now you've really got me intrigued. What could be more extreme than a supernova?
We're venturing into the realm of the truly bizarre now.
Uh-oh.
I'm talking about neutron stars and black holes.
Neutron stars and black holes? Now, those are names that send shivers down my spine.
They are objects of incredible density and gravity, pushing the limits of our understanding of physics.
Tell me everything. Where do we even begin?
Let's start with neutron stars. Imagine squeezing all the mass of our sun into a sphere the size of a city. That's a neutron star. They're so dense that a teaspoonful of neutron star matter would weigh billions of tons.
That's just, I can't even wrap my head around that kind of density.
It's mind-boggling, isn't it? And these neutron stars, they're spinning incredibly fast, some rotating hundreds of times per second.
So these are like cosmic spinning tops, but on a scale that defies imagination.
A very apt analogy. And then we have black holes, regions of space-time where gravity is so strong that nothing, not even light, can escape.
Black holes, the ultimate cosmic enigmas.
They are, and their formation is fascinating. If the collapsing core of a star is massive enough, even the incredible density of a neutron star can't withstand the gravitational crush. It collapses further, becoming a singularity, a point of infinite density.
A singularity, and that sounds terrifying. So how do we even know black holes exist if we can't see them?
We can't see them directly, no, but we can detect their presence through their gravitational effects on the surrounding matter. It's like seeing the footprints of a ghost, knowing it's there even though you can't see it directly.
That's incredible. So what determines whether a dying star becomes a neutron star or a black hole?
There's a critical threshold called the Chandrasekhar limit. It's a mass limit. If a white dwarf exceeds this limit, it collapses into a neutron star or a black hole.
So the Chandrasekhar limit is like a cosmic tipping point, determining the fate of dying stars.
Exactly. It's a testament to the power of physics and mathematics to help us understand the workings of the cosmos, even at its most extreme.
This is all so much to take in, but I'm loving every minute of it. From nebulae to supernovae, white dwarfs to neutron stars and black holes, the life cycle of stars is a story of cosmic drama on a scale we can barely comprehend.
Absolutely. And this journey through stellar evolution has only just begun. There's still so much more to explore. Stay tuned for part 2 of our stellar evolution saga. We'll dive deeper into those stunning planetary nebulae, unravel the mysteries of the Chandrasekhar limit, and delve into the mind-bending physics of neutron stars and black holes. You won't want to miss it.
Welcome back to the Deep Dive. Before we continue our exploration of stellar evolution, I'd like to revisit those planetary nebulae we touched on earlier. They really are quite remarkable. Yes, those cosmic works of art that you mentioned,
Right.
those are the ones that really make you just want to grab a telescope and spend all night staring at the sky, right?
Precisely. Imagine a star similar to our sun reaching the end of its life. It's exhausted most of its nuclear fuel, it's expanded into a red giant, and now it's shedding its outer layers into space, creating this stunning visual spectacle.
But those outer layers are what form the planetary nebula.
Yes.
It's like the star is shedding its skin, revealing something new underneath.
That's a great way to think about it. These expelled layers form a glowing shell of gas and dust around the star's remaining core. And when I say glowing, I truly mean it. The central core, which will become a white dwarf, emits intense ultraviolet radiation.
So it's not the star itself that's glowing, but the gas around it that's being lit up, like a cosmic fluorescent light.
A perfect analogy. And the shapes these nebulae take are just as fascinating as their colors. They can be round, elliptical, bipolar. Some even resemble butterflies or hourglasses. The possibilities are endless.
It's like each planetary nebula is a unique fingerprint, a cosmic signature of the star that created it.
Yeah.
You mentioned some famous ones.
Absolutely. One of the most well-known is the Helix Nebula. It looks like a giant eye staring back at us from the depths of space. There's also the Cat's Eye Nebula, known for its intricate concentric rings.
I've seen pictures of those.
Mm-hmm.
They're truly breathtaking. It's a reminder that amidst the vastness and the darkness of space, there's also incredible beauty.
And it's not just about aesthetics either. Planetary nebulae, they provide valuable insights into the late stages of stellar evolution.
Oh.
By studying them, we learn about the processes that occur when stars, like our sun, reach the end of their lives.
Speaking of the end of a star's life, let's revisit that Chandrasekhar limit you mentioned earlier. You said it plays a crucial role in determining whether a dying star becomes a white dwarf or something far more dramatic. Can you elaborate on that?
Of course. The Chandrasekhar limit, named after the brilliant astrophysicist Subrahmanyan Chandrasekhar, is essentially a mass limit for white dwarfs. It's about 1.4 times the mass of our sun.
Okay, so if a white dwarf is below this limit, it remains stable, slowly cooling down over time?
Exactly. It continues to cool and fade over billions of years, eventually becoming a black dwarf. But if a white dwarf exceeds this limit, things can get a lot more interesting.
You're talking about supernovae again, right? Those spectacular explosions that scatter heavy elements throughout space.
Precisely. Let's say you have a white dwarf in a binary star system where it's pulling matter from its companion star.
Okay.
As it accumulates more and more mass, it eventually crosses the Chandrasekhar limit. At that point, the white dwarf can no longer support itself against gravity.
So it's like a cosmic pressure cooker.
Yes.
Too much mass, too much pressure, and boom.
That's a great analogy. And the result is a Type Ia supernova, an incredibly powerful explosion. But remember, we also talked about Type 2 supernovae, which occur when a single massive star runs out of fuel and collapses.
Yes, those are the ones where the core implodes and then rebounds, causing a massive explosion.
Right. Well, the Chandrasekhar limit also plays a role in those scenarios, but in a slightly different way.
Okay.
When a massive star collapses, its core can become a neutron star, but only if it's below a certain mass limit.
So the Chandrasekhar limit helps us understand what determines whether a dying star becomes a neutron star or a black hole.
Exactly. If the collapsing core exceeds about 3 times the mass of the sun, even the incredible density of a neutron star can't withstand the gravitational pressure.
And that's when you get a black hole. It's like gravity wins the ultimate battle, crushing everything in its path.
Precisely. It's a concept that really pushes the boundaries of our understanding.
Yeah.
A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape its grasp.
It's like a cosmic abyss, swallowing everything that ventures too close. I'm getting chills just thinking about it.
It's a powerful image, isn't it? And while we can't directly observe black holes, we can detect their presence through their effects on the surrounding matter. It's like seeing the shadow of something that's invisible.
That's amazing. So we see the evidence even though we can't see the black hole itself.
Right.
It's like a cosmic detective story.
Indeed. And the story of black holes is intricately connected to the life cycle of stars.
Yeah.
Those massive stars that end their lives in supernovae, they seed the universe with the heavy elements needed to form new stars, planets, and ultimately life itself.
It's a beautiful and awe-inspiring cycle. From the birth of stars in swirling nebulae to their dramatic deaths and the remnants they leave behind, stellar evolution is a testament to the vastness, the complexity, and the wonder of the cosmos. Wow, we've covered so much ground in our exploration of stellar evolution. It's amazing to think that something as seemingly simple as a cloud of gas and dust can give rise to something as powerful and complex as a star.
And from those stars, we get everything that makes up our world, even ourselves. It's a humbling and awe-inspiring thought, isn't it?
It really is. We started with those vast nebulae, the birthplaces of stars, and then we followed their journey through the main sequence, the red giant phase, and for some, the dramatic finale of a supernova. We even touched on the incredible remnants they leave behind, those mind-boggling neutron stars and black holes.
Right. And throughout this cosmic journey, we've seen how the Chandrasekhar limit acts as sort of cosmic gatekeeper, determining the fate of dying stars.
You know, it's fascinating to me how something as seemingly abstract as a mathematical limit can have such a profound impact on the universe. It's a testament to the power of physics and mathematics to help us understand the workings of the cosmos.
Absolutely. The Chandrasekhar limit shows how, even in the most extreme environments, there are underlying principles governing the behavior of matter and energy.
And it underscores the interconnectedness of everything in the universe. The death of one star can provide the building blocks for the birth of new stars and planetary systems, a cycle of cosmic creation and destruction that's been playing out for billions of years.
And it's a cycle that continues to this day. Every time you look up at the night sky, you're seeing the light from stars that have lived and died, their remnants scattered across the vastness of space, contributing to the cosmic tapestry that we're all a part of.
This deep dive into stellar evolution has truly expanded my understanding of the universe and our place within it. It's given me a newfound appreciation for the intricate processes that have shaped the cosmos and made our existence possible.
And as we wrap up our exploration, I encourage you to keep looking up at the night sky with a sense of wonder and curiosity. There's still so much to discover out there, so many mysteries waiting to be unraveled.
So the next time you gaze up at those twinkling points of light, remember the incredible stories they tell, the cosmic drama that's been unfolding for billions of years.
And remember that we are all part of this grand cosmic story, connected to the stars in ways we're only beginning to understand.
Thank you for joining us on this deep dive into the fascinating world of stellar evolution. We hope you've enjoyed the journey as much as we have. And until next time, keep exploring, keep questioning, and keep looking up at the stars.